Good afternoon. Welcome to the class. I'll be writing notes here for the agenda and what's due. What's due is homework 5, the last required homework here. The extra credit optional homework as well as the lab will be posted later today. And of course, project 2B is still due. I think it's due May 1st, right? While we get chalk, can you take a quick poll on where you are on your project?
Oh, it's just released.
Alright, so I don't have a chalk. Someone's gonna create a slide here. So that's your options, A, B, and C. What's that one?
Here is like where they're showing this kind of here is just run on just like it. That is data. It's called hey, I mean, you have one you mean I yeah. It's not good, it's a hard one. Is it all complicated?
Alright, there we go.
So that's for part 2B,
Yeah.
that's sort of the same as for part 1.
Yeah. There might be a couple of private tests, but the public tests are the same. Yeah.
But you said the public test was
Okay, is that all we have? 70 records? 75.
I mean, I haven't submitted.
Everybody done?
that.
Okay, we have this meeting open, there's about 75 plus people, and 55% say they're passing 0 tests or not started yet. I'm not sure how that's possible, because I think at least, actually strictly over half the class was passing at least 10 tests in part A, which means they will automatically pass that many tests in part B as well. The tests are identical, all right? So I'm not sure why. It could be just the sampling of the class. The class is about 125, slightly over 125, and we only have 77 figures here, right? So that could be an explanation. The tests are indeed identical. On Piazza, I posted a mathematical analysis note. I strongly encourage you to carefully read it. It's useful for your conceptual understanding of reliable transport protocols, pipelining, and so on as well, independent of the project. And it will also help you in the project where, in the following sense, if you're testing your code with some channel parameter settings, using our server or running the server yourself, which is trivial, which you know how to do now, first step of the project, you don't quite have a sense of how much room is there for optimization, right? That's the key. With our tests, we're not making the test parameters public. That's by design, right? It's more like an exam. That's how it's meant to be. But parameters to whatever you want in your own tests. And as long as you're performing, as long as you get to a point where you don't see much more room for improvement, I think that's a good goal to strive for. You would have very likely achieved the project's requirements. Another alternative, of course, to upload your code and see where you stand on the leaderboard, right? But that doesn't really tell you like how much your performance should be. But doing your own tests, using that note, here's a note that I posted. If these are the parameters of the channel, what can you expect in the best case? Gives you a sense of how much room there is for optimization. If there's 10x room for optimization, it clearly means that you're not using pipelining at all. For project A, for correctness, we strongly encourage everyone to use a stop and wait protocol because it's easier to implement in debug. There's enough complexity there that moving on to speed, which is pipeline, is what gives you the speed. It's favoring complexity of design and hardness of debugging over correctness, which would have been wrong for 2A. But for 2B, you need a pipeline protocol for speed, right? So keep that in mind. Well over half the classes passing in 2A at least 10 tests when I checked last on the leaderboard. So that should be the case for part B as well. At this point, in part B, it's a two-tuple that's going to matter: your correctness score and your speed score. This is all explained in the two Piazza posts related to 2B. It doesn't matter. Your speed is not. Your speed is a secondary metric, right? So if we compare it's a competitive setup on the leaderboard. Compare two submissions, one of which passes 15 tests, another passes, let's say, 13 tests. And no matter how fast either one of them is, this one dominates this one. Okay. If two submissions both pass, let's say, 14 tests, then the speed metric comes into play. So part B is both correctness and speed. And so this is all explained. I'm never sure how many people actually see the Piazza posts that I wrote. I'm going to stop this. But this is a fairly long note that would be very, very useful conceptually for you. And here is a note that tells you how the leaderboard presentation will be. I don't think you can read it here. So see it clearly enough. Yeah.
So the grade for 2B is it like you have a 100 if you pass all the tests and then like your leaderboard score is out on top of that, or is it like combination of both?
Can you repeat the question again?
So is your score like, you know how like in project 1, like it was based off your grade scope score and then like you get like a speed metric where you have.
Yeah.
So it's like a combination of speed and
Yes.
accuracy for your final score.
Yes. So let me just show you. I think I can show you the leaderboard because that's something you can see yourself too. So I'm not violating any FERPA laws here. Sorry. Okay. So that's how the leaderboard looks. And if I go to, I'm also going to show you what our project 2A looked. This is all described in the Piazza post as well. Okay, if you look at 2A's leaderboard, these are there's only one metric, right? All right, that's the accuracy metric. So these are all the submissions passing all 16 tests. If you look at time, this took 566. This actually is faster at 408. But this column really doesn't mean anything in 2A because we only are looking at correctness, right? In 2B, accuracy and time are combined into a score. Again, this score is not some 10 times your final score out of 100. Right? This is all plentifully explained why we cannot give you a final score with an autograder that's just a dumb program, right? But the thing to notice is here all the times are in sorted order. So all the 16, everybody who's passing all 16 public tests will have their times in the sorted order. So this is the number 1 submission, this is number 2 submission, and so on. And the mathematical analysis note tells you in great detail why we cannot possibly give you a target. Like this is your speed, you get 100. Well, we just cannot do that. And you should read the note to understand why. We don't know how well you guys can perform. But at a high level, the reason simply is if we set an arbitrary, any target we set would be arbitrary, and if not even half the class gets there, it doesn't make any sense. We'll have to change the target anyway, right? So what I wrote in the posts is what I do for the grading overall. Remember I told you grade expectations as a post about it, at least 1/3 of the class will get one of the A grades. So it's a similar competitive setup here where I can guarantee that if you're in the top third of the class, you will get 100, top third in the leaderboard, okay? And I can only guess, I don't know this, that if you're not in the top half, you'll probably not get 100. But the scores will gradually taper. So somebody who is sort of here and the 100 cutoff happens to be, let's say here, this next submission will probably get 99.8 or something like that. So it'll go all the way from whatever is the cutoff between 1/3 and 50% likely. The 50% part is not fixed, but at least 1/3 will get 100. We will go from 100 all the way to 0 as the score, the accuracy and time goes to 0, and 0 means you're not passing any tests, which means your time is going to be infinite, right? So as we go from 16, whatever, or it doesn't have to be 16, our cutoff could be, cutoff will be at 16, and at least 1/3 we know will be passing 16 tests because they were already passing that in 2A. As we go from 16, whatever time is the cutoff, which we don't know, to 0, infinity, your scores will go from 100 to 0, alright? So passing at least one test is trivial. If you simply just wrote the most basic hello world, you read the project description, wrote the a simple hello world UDP program, send one UDP datagram, you will pass a couple of tests actually, alright? There's at least a couple of tests that have a tiny amount of content with a perfect channel. Nothing bad is actually happening in those tests. It is simply testing that you read the description and you're on your way to doing something. So there's no reason for anyone to be here, alright? If you spend half a day, there should be no reason for you to be here. Okay? That's going to be the grading scheme. Make sense? Yeah. What this cutoff is, read the note to understand why there's like a 10x variation in how your speeds could be. So it doesn't make sense for us to just draw a line somewhere arbitrarily. Other questions? Yeah.
So if 1/3 of the class is, if only 1/3 of the class was able to pass all the tests, does that mean that 1/3 is guaranteed to get one of the A grades for the project?
1/3 is, well, we already know that 1/3 of the class is passing all correctness tests. That was more than 1/3 were passing in 2A. They will be passing in 2B as well. So we already know that. So I'm comfortable sort of guaranteeing. The requirements for 2B is, for 100 is you got to pass all the correctness tests. And you got to be sort of faster than a stop and wait protocol, right? It's similar to saying in project 1, remember, your correctness, your file had to be downloaded correctly. And you had to be faster than the 2 minutes of the client server time, right? The faster you were, the more points you got. So it's very similar setup to that. In project 1B, it was easier to approximately guess a cutoff where we expect you to be. But here it's much harder. These tests are also different. Grade scope environment is different. So we can't possibly give you a cutoff for that. But we already know that more than 1/3 are passing all tests. And even if those 1/3 or so, whatever speed they get, they're guaranteed to get, the top 1/3 is guaranteed to get 100. Right? So that's what you can be sure of. And the rest, it doesn't mean there's going to be a steep fall off. It'll be a gradual fall off. There's a huge amount of room for improvement from here to here. So it'll just gradually fall. If there's, let's say, 40 students between 100 and 0, then it'll linearly fall off and it's about 2.5 points per student as you go from here to here, right, on average. That's the way to think about it. So it's a competitive setup. That's why I call it a race, not a time trial. Those of you who are into running, cycling, or sort of swimming, athletic kind of sports, there's a difference between a race and a time trial. When you're running in the Olympics, it doesn't matter whether how close you're to the world record time or whatever, right? All that matters to getting medal is that you're faster than the people around you. You could be beating the world record, if one of them is also beating the world record, they're faster than you, then you lose. So it is a competitive setup, and it comes with a necessity caveat that we don't have an exact cutoff for what is 100. And I would also say the cutoff really it's not going to make any difference to your final grade. It's psychological. So if you happen to, there'll be a couple of students who fall at the boundary of 100 who will get just under 100. They might get 99.8, 99.9. It's purely psychological. It's going to make zero difference to your final grade. Grade boundaries will never be drawn sort of distinguishing it, that percentage of overall grade. But I understand that some people get psychologically very impacted to know that they were imperfect, right? So 99.9 is not like basically 100, it's more like, I'm not perfect. Just get out of the mindset. It doesn't really matter. Right? Do your best, right? That's the best way. Anything else? Okay, today's topic. We're doing the link layer. I left off here, right? Slotted Aloha. I told you a very important problem was this multiple access problem. So we are continuing with MAC problem. We will look at So I gave you a human analogy for how with even just 2 nodes, we can have interference if on a long distance call or a satellite call, right? The analogy, or the reason that happens is fundamentally because of delays. A simple protocol like the polite conversationalist protocol, speak only when no one else is speaking, works pretty well, but not perfectly, right? In fact, Ethernet also uses a simple protocol like that, which is, it starts out by speaking. A node starts transmitting only when no one else is transmitting. But it doesn't solve the problem of collisions because immediately after one node has started talking, the other node can also start talking before this node's signal reaches the other node. And then they mix in the wire. If the bits overlap in the wire, that's when garbage goes in both sides. They cannot equal the packets, right? These are literally electromagnetic waves combining together, and the CRC's cyclic redundancy checksums are going to fail. Okay, so Aloha has a probabilistic design, which is if a node has something to transmit in a slot, it's going to first go ahead and start transmitting. It's going to take the first frame, transmit that in the next available slot. They have some mechanism to detect collision. I'll tell you how Ethernet works. In wireless, it's a little different. If they figure out that this frame that they just sent collided, which means nobody has got anything, then from the next slot onwards, they will enter a probabilistic backoff mode, which is in the next slot, they will toss a coin that shows heads with probability P. If it shows heads, they're going to transmit. If not, they'll again toss the coin until it shows heads. When they get to a point where they are successfully transmitting, at that point they get out of this collision mode. At that point, they don't have to be probabilistic. So if you go back to our goals, our blind senator problem goals, or the random access problem goals, when one node wants to transmit, it should be able to use all the channel capacity, all the bits per second bandwidth. That is true. There's only one node transmitting in Aloha. It's going to transmit in the first slot. No collision will happen because nobody else is trying to say anything. Second slot, third slot, and so on. No problem. What happens when n nodes want to transmit? Right? Our goal is fairness. You got to take a channel capacity R bits per second, and divide it equally amongst all the available nodes who want to speak, which is a dynamic quantity, right? N could be less than n, the total number of nodes. Not everybody may want to speak, but resources should be shared fairly amongst the ones that do want to speak. So let's look at how Aloha does on that metric. It's not great, right? Ethernet is much better than that. But here's where we need some math for Aloha, or slotted Aloha. It's called slotted Aloha because the slots require clock synchronization, which is not a free assumption, that has a cost. We will remove that assumption in just a minute. So it says here that the efficiency, what is the efficiency? Let's go back to these two slides. Here we can see that some slots, nothing happens. So slot 1 is wasted because of the collision. Slot 2 is wasted because nothing at all happens. Just nobody's trying to sync. Slot 3 is wasted because of collision. Slot 4 is successful. So amongst the 1, 2, 3, 4, 5, 6, 7, 8, 9, the 9 slots, the first 9 slots here, slot 4 does something useful, slot 8 does something useful, slot 9 does something useful. So 3 out of 9 slots are doing useful work, which means exactly 1 node transmitted in that slot, which is our goal, right? That is the multiple access problem. So in this example, the efficiency is 3 slots out of 9 slots, 1/3. 1/3 is not great, right? In this example, it is 1/3, but what can it be in general? It turns out that in general, Aloha's efficiency is actually not far from what's shown in that picture. In the limiting case, its efficiency is about 37%. So if you have a 10 Mbps channel, Aloha is going to give you 3.7 Mbps, 37% of 10 Mbps. Okay. It's not terrible. I mean, it is simple, it's decentralized, it is efficient when only one node needs to transmit. And we can remove the clock synchronization requirement shortly, alright? But the efficiency, if 5 nodes want to transmit, they should all, in a 10 Mbps channel, they should all get 2 Mbps each. That's not being satisfied by Aloha. How do we show that Aloha has its efficiency of 37%? And where did E come from? What is E? E is a mathematical constant like pi, right? What's its value? Well, 1/E is that, so you know what its value is. It's about 2.7, 1828, and so on. How did E come about? We need a little bit of probability. So this is the second place in the course after the very first chapter 1, where we looked at some circuit switching versus packet switching, that we did some probability, right? Here's another place where we'll need some very basic, similar probabilities to that. So let's assume that there's n nodes that are all trying to send frames. They all want to speak. These are all like our blind senators dying to express their views in the Senate. And they've all collided, so each of them is in a probabilistic mode. We're just making this assumption for simplicity, right? If there's many nodes, very likely they will always be in collision mode. They'll always be in this probabilistic transmission. In every slot, they transmit with probability P, right? So here's the probability that a given node has a success in a slot. So this is like saying, what is the probability node 7, and assume node 7 is one of the n nodes that's wanting to transmit. What is the probability that node 7 is successful in a slot? Not any node, a particular node, a given node. Well, it is the probability that that node transmits in that slot. That event's probability is P. And node 1 does not transmit, and node 2 does not transmit, and node 3 does not transmit, all the way to node 6 does not transmit, and node 8 does not transmit, all the way to 9, and all the way to n does not transmit. Node 7 transmits, and none of the other nodes transmit. That probability, the first event is P. All these events are independent, so the probability is just going to be multiplicative. Right? So that's how you get that value. What is the probability that some node is successful in a given slot? this is the probability that node 7 is successful in a given slot. What is the probability that just any node 7 or node 6 or just any node is successful in a given slot? Yeah? Yeah, you multiply that by n because it's a union of a certain number of events. The probability that any node or some node, I mean the same thing, right, in English, is successful and math is successful in a slot is given by either node 1 is successful, or node 2 is successful, or node 3 is successful. And these are all exclusive events. It's impossible that node 1 is successful and node 2 is also successful, right? That would be a collision. So each of those events has this probability, and there's n nodes, and these are n mutually exclusive events. So the OR of all those events happening on those events is an event whose probability is the sum of those individual probabilities, right? So that's why you get the probability that any node is successful, or this equivalent, you can read that. This is the probability that a slot is successful, which means exactly one node is constant. Okay. Still, how did we get E? E is this transcendental, this irrational number. We're going to take the limiting case as n tends to infinity, which means more and more and more nodes are competing for access, and ask, what is the value of P that maximizes this expression? I didn't say what P is. P is a parameter of the protocol. It's the parameter of the local protocol. You could set P equals some constant, right? You can say P, let's say P is 10%. Is that optimal? In general, that's not optimal. So you want to ask the question, what is the optimal P setting that maximizes this expression? How would you find that? You've learned this in your math courses. These are required math courses for CS. How would you find the value of P that maximizes this probability? Yeah, you've learned this in your calc courses. To maximize a function, you're going to take the derivative, set that to 0, and then check the second derivative that it's a maximum equals to a minimum. Sometimes you can have multiple, you might be looking for a global maximum or minimum. You don't have to do all of this. That's what we do. In this case, it only has one maximum, and it's easy to know that that's a maximum by checking the second derivative. So that's all you do. You set the derivative, set it to, take the derivative, set that to 0. And solve for P, which will give you a P star value. So given an n, you will get a P star by taking the derivative and setting it to 0. Whatever value of P you got, we call that P star. That is the P star. That is a probability parameter set that will maximize efficiency with n nodes, where n is given to you. And now we simply ask the question of, as n tends to infinity, this P star is going to be some function of n. Okay, when you take the derivative set it to 0, you get P star in terms of n. When you plug back that P star, which is some function of n, back into this expression and ask, what happens if n tends to infinity? As there's many, many, many nodes competing for slot at a low access, then the limit of that expression, n P star times 1 minus P star minus 1, where P star is replaced with whatever value you got by maximizing this. That limit value goes to 1 over e. Okay? That's how we got E. And E also happens to be, why does the strange number E come about? Because E's definition is I believe it's this limit n goes to infinity. Somebody could sanity check it. I don't remember off the top plug in the value, the expression will look like that, that's what E comes from, okay? Just E is, that is E. Okay, so that is slotted Aloha. Questions? I told you we could remove the time synchronization requirement. Time synchronization is not free, it's not cheap, it costs something. And we can make pure Aloha or unslotted Aloha. At the cost of some efficiency, we can remove the time synchronization requirement. So in this picture, this shows you the collision probability when there is no time synchronization. When nodes don't know where a slot starts and where a slot ends. Or they each have their own notion of when a slot starts and when a slot ends, but their clocks are not synchronized. This is the real world. In distributed systems, you don't have a central clock. It is not possible to have perfectly synchronized clocks in the real world. The difference, the small error matters. It's impossible to make that error zero. And that small error does matter. So in this example, it shows you how the green frame is colliding with the yellow frame, and the yellow frame is colliding with the purple frame, right? And we can compute this probability, this efficiency, by, the textbook shows you this very simple modification of math in the previous slide. We want, when a node is transmitting, we want no other node to be transmitting in the immediately succeeding slot or the immediately preceding slot, because if they are, they could be potentially overlapping. That's the adjustment we need to make to the math in the previous slide. And that makes it go from 37 to basically half of 37. The answer changes by 1/2. That's how you get 18%, right, across. So that's the efficiency of unslotted Aloha. So where are we now? If one node wants to transmit, it gets all the channel. We met that goal. It is simple and decentralized. No clock synchronization. But its efficiency, if our nodes want to transmit, each should get a fair share of the channel. Well, each is getting 18% of the fair share of the channel is what's happening. Or they might get as low as 18% in the limit case, when a large number of nodes are competing, which is very unsatisfying. Okay, but Aloha is an important protocol because it's a precursor of Ethernet. Ethernet is based on this idea, on the same random access for the multiple access problem idea, and it actually is pretty efficient. It's much more efficient. And we'll see how to compute, how to analyze Ethernet's efficiency. We won't derive Ethernet's efficiency. It's not too hard, but we don't do that, of course. Ethernet is based on the idea of carrier sense multiple access. We have now all the principles we need to understand how Ethernet works. It is maybe the single most important link for a protocol. It is that Ethernet cable and Ethernet port, which all of you are familiar with, is used to even lay people out, right? They kind of recognize what it is. What's happening in the NIC is it's speaking this Ethernet protocol. And the multiple access part of it, that is CSMA. It's actually called CSMA CD, Carrier Sense Multiple Access with Collision Detection. Let's look at the carrier sense multiple access, or CSMA part of it. The first rule is the rule of being the polite conversationalist, which is if somebody else is talking, don't talk. Okay, mom taught us this, and that's what Ethernet does to begin with. The second is if somebody is talking right now, its channel is busy, which is what the carrier sense means. Ethernet NICs can sense the carrier, the wire, to see if there's something on the wire. They don't need to know there's bits on the wire or what bits they are. They just need to measure the energy. If it's above the noise floor, that means something is on the wire. That's all they need to measure. That's all they need to sense. They don't need to decode or anything. They don't need to go to bit line. Okay? They don't even need to go to signal line. It's just measuring energy. If it's busy, then you defer transmission. That's carrier sense multiple access. CSMA CD is what Ethernet does. This is not enough. Why is this not enough? Same reason. You can start talking, and not necessarily the same, and even shortly after another one can start talking, before the signal got there, which takes propagation delay time, and at that point, bits can mix. If even one bit overlaps between two frames like this, then it may break the CRC checksum, then nothing will get encoded. So CSMA CD is carrier sense multiple access with collision detection. If you were being applied convolution was transmitting only when the channel was idle and still encountered a collision, which can happen because of propagation delays, then you are going to abort. As soon as you detect that a collision is happening, you're going to abort the rest of the frame. There's no point transmitting a frame if you know that some collision has started happening. So you'll cut short your frame transmission. And after that, you're going to back off for a random amount of time. Let's first make sure that we understand the physics of this before we look at the entire CSMA CD algorithm. Okay, this is the high level. You start out being applied convolution. If collision still happen, you will abort and then back off for a random amount of time, just like here in the convolution. So, excuse me, here's a picture. Collisions can happen with carrier sense. Will stop the entire packet transmission from getting wasted. So here it shows me node 2 has started transmitting at time 0. Time is going down, okay, vertically. And space is laid out. It's just a single, let's say a chain topology, simple graph. Just a single cable with 2 connectors to which 4 nodes are connected. So node 2 starts transmitting at T0. And the signal has reached as the width of that yellow beam tells you how much distance the signal has covered until that time. At this time, so this node 2 is being applied convolutions. But at this time, node 4 can also start transmitting because the signal from node 2 hasn't reached node 4. It's between 3 and 4. It is getting there at this time. But at this time, node 4 didn't know that node 1 had started speaking, and it also started speaking. That's what can cause collisions, because propagation delays are non-zero. It's what can cause collisions even if each node is trying its best to not speak when others are speaking. At this point, on the wire, the yellow and red bits are mixing, which means nothing can get decoded. In fact, these bits can also not get decoded, even though it looks here like this didn't mix. It's true, it didn't mix, but the thing is, this whole thing is a frame. Frame is being transmitted over its transmission delay, size of the frame, where the speed of the link, this entire time. If any bits get corrupted, checksums will fail. So the entire frame is going to be waste. There's no point continuing. This is the point when, this is the point when node 2 detects there is a collision happening. How does it know it's a collision happening? Because it knows the energy is dumping on the wire. It can simultaneously sense the energy on the wire. If it senses the energy on the wire is different from what it is dumping, there is some positive or negative cancellation happening. Okay. And so at this point in time, node 2 can determine that there is a collision, and at this point in time, node 4 will determine that collision has started happening. They will wait for a little bit of time to ensure that collision is happening. They'll sense it for a short period of time to know that, okay, there is indeed a difference. There's a persistent difference between what I'm transmitting and what is on the wire. So this must be because somebody else is also transmitting. And at that point, they are going to abort the transmission instead of following. So this would be how they follow. This is when, had they followed through the transmission. Instead, they're going to cut short their losses and say after this much of collision detection time, they're going to abort the transmission. There's no point sending the rest of the frame because they've detected that that a collision is happening, so it's going to be not decodable by it. This is carrier sense, multiple access with collision detection. Well, a collision happened, what do? Well, you do the same thing as aloha, which is what happens when an aloha collision happens. We enter a probabilistic transmission mode. What do you do here? Well, it is probabilistic, but the implementation detail is a little bit different. Here's the Ethernet's full CSMA CD algorithm. Well, let's ask the question of, in a human conversation, when I said, let's say two people are talking and they collide, and then they both decide to let the other person speak. There's silence for a little bit, and one person says, you go ahead first. And let's say that also collides because both say, you go ahead first at the same time. And again, there's going to be some silence until somehow one person resolves, goes ahead and actually says whatever they were trying to say, and the other person simply listens. So when I asked how in the last class, how we do this as humans, all people said randomization. But randomization has different ways of doing it. In Ethernet, well, in a real conversation, if you think about it, if a collision happens 2 or 3 times, this process of you go ahead and saying that also simultaneously results in a collision, we are going to wait longer and longer periods of time. If you both collide at you go ahead, you're probably going to wait longer than we waited the first time. And again, one person then may try to grab the tongue and start speaking. If again there's a collision, we might wait for an even longer period of time. That's what we do in human conversation. And that works pretty well. That's exactly what Ethernet does. So here's a stepwise Ethernet complete Ethernet protocol. The NIC receives a frame, a datagram from the network layer. So the TCP or UDP encapsulated in IP goes down to the link layer. And it's ready to be sent on the NIC. It senses the channel. If channel is idle, it will start frame transmission. Okay. That's our polite communication protocol. If it's busy, it's going to wait until the channel is idle and then transmit. If it can sense the channel is not idle, it will never transmit, but we know that this is not enough. If NIC transmits the entire frame, starting from the idle channel, it happens to be lucky, no collision happens, NIC is done with the frame. But like in the previous picture, on the previous slide, if NIC detects that another transmission is happening because the energy is putting on the wire is not the same as what it senses on the wire, mid-frame transmission, it's going to take a short amount of time to be certain that that's happening by sensing it for that period of time. It's going to then abort the transmission and then send a jam signal to tell other nodes that there is a collision that just happened right now. Not a single node determining that there is a collision that's happening. It doesn't mean that other nodes necessarily know. This node knows that what it's sending is not the same as what it's hearing on the wire, but other nodes are not sending it. They don't necessarily have the same information. It's good for everybody to know that there was a collision just now. Okay? So both aborts and sends a jam signal which is indicated there is a collision right now to everybody else. And after aborting this NIC transmission, it enters this binary or exponential backoff. Exponential backoff means so it's not quite Aloha's slot transmitting in a slot with P. There's no notion of slots. Instead, it will stay silent, back off for some time. And again, try. If there's again a collision, it will double the back off and wait for a longer period of time. These times are randomly chosen. They're not fixed constants. Because if they're fixed constants, everybody will keep trying again at the same time. That's not useful. They will randomly choose it from some interval. That interval keeps on increasing. So the expected back off time will keep on doubling. And it's working as follows. After the mth collision, after m collisions, the NIC will choose a number, k, at random from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 2 to the n minus 1. So after the first collision, it will choose a number between 0 and 1. So it will wait for either no slots, try to wait transmit, or wait for one slot. This slot, by slot I mean just a fixed period of time. Okay, it's really the value of this is 512 transmission times. That's what the value of that time is. If it tries again there's a collision. It will now wait for between 0, 1, 2, 3. It will pick a random value between 0, 1, 2, and 3, and then wait for that many 512 bit times. I'll explain what 512 bit times means in a second. There's a third consecutive collision, it will pick a number between 0 to 7. Fourth consecutive collision, 0 to 15, and so on. So in expectation, after 4 collisions, each node is, for consecutive collisions, each node is waiting for about 7 or 8 of these slots. But it's unlikely that they will both pick the same number, because the first node might wait, if it picks a random value between 0 and 15, it might pick 2. The second node might pick 9. And so they wait for different amounts of time, so one node might eventually get in successfully transmitted. Remember that it doesn't have to they don't have to even be a part of the full frame transmission time. They just have to ensure that when they eventually get to a point where one node transmits, no other node also transmits close enough such that this first node's transmission signal doesn't reach them. If it reaches them, they will apply the polite convolution protocol, don't send me something else is sent. Okay, so that's what's happening. This is exponential backoff. What is this? It waits for k times. The k is chosen from the doubling intervals. What is 512 bit times? A bit time is just a bit transmission time. It is a time to transmit 1 bit on the wire. So on a 10 Mbps channel, 1 bit time is 1 divided by 10 times 10 to the 6 in megabits per second. On a 100 bits per second channel, 1 bit time is 0.01 seconds. On a 1 kbps channel, 1 bit time is 0.001 seconds. So bit time is 1 bit's transmission time. So it's really just 1 over capacity in bits per second of the channel. And 512 is just a constant infinite. It's sort of like saying a frame is about 512 bits on average. It doesn't have to be, it's sort of making that much more. It could be a little more, a little less, but it's part of the standard, it's a reasonable number. But the k is what's doubling, or the interval from which k is chosen is exponentially increasing over time with consecutive collisions. That's it, that's all it's even at. Yeah.
What if the jam signal collides? Can it collide?
Let's go back to this picture. It's a good question. So a jam signal is just a certain fix. It is possible, it's a repeating pattern of bits. So if all nodes are avoiding transmission after the short detection period and then following after that with a sufficiently long jam signal, it will be detected, at least the tail of it, some tail of it will be detected. Okay? That jam signal doesn't even need to be decoded as an Ethernet frame. It's sensed at a lower level. So it just has to be long enough to make it extremely unlikely. I mean, what is long enough? That depends on how long this wire is, how long likely it is to go from one node to another, right? So maybe you'll have a better appreciation for how the length of the cable matters with the efficiency numbers. Right, so that's the answer to the jam signal. We can ask this question of what is Ethernet's efficiency, just like we did for Aloha. In Aloha, we said slotted Aloha has 37% efficiency in the limiting case, when a large number of nodes are interfering. Unslotted Aloha is worse, it's 18%. We were unsatisfied with that. And told you Ethernet's much better. What is Ethernet's efficiency? Ethernet's efficiency is given by that formula, 1 over 1 plus propagation delay divided by transmission delay. So let's do some sanity checks on this expression. Intuitively, if two nodes are very far apart on a satellite net channel, so long propagation delay, do you think the likelihood of collision is higher or lower? Yeah?
Higher.
Higher, right? I mean, we saw a video, a parody video the other day for that. It's intuitive that the longer the propagation delay, the more the likelihood of collision, because the signal from when one person started talking will take a long time to get to the other side. If the cable is, the distance of propagation delay is long. And in that time, this node can also start speaking to the collision. So long cables, long Ethernets, long propagation delays means more collision. More collision means less efficiency. More slots are going to be wasted. So in this formula, which is 1 over 1 plus 5 times, right? Yep. 5 times T top times propagation delay is high if it's a 1 meter Ethernet as opposed to a 100 meter Ethernet, single room Ethernet as opposed to a large building Ethernet. The larger the Ethernet spread, the longer the cable, the longer the propagation delay, the longer light speed it takes to go from one end of the network to another end of the network, the less the efficiency. That's intuitive. This is saying, what is this? This is the transmission delay. What is transmission delay? Size of the frame divided by speed of the link. So this is saying if transmission delay is high, efficiency is high. This is in the denominator, so it's essentially like the efficiency, this formula is saying, increases with higher transmission delay. That's strange, isn't it? That means efficiency increases if it's a low capacity link. So a 10 Mbps Ethernet is more efficient than a 100 Mbps Ethernet, which is more efficient than a 1 Gbps Ethernet and so on. Why? Because the lower the Ethernet speed, the higher the T-trans. The higher the T-trans, the higher the efficiency. Let me move aside so you can look at the formula. Why would this be? If you send big frames, or if the Ethernet itself is a slow Ethernet, it'll be more efficient. Yeah?
Because if a large frame goes through successfully, you can occupy the wire for a longer period of time. So you're utilizing the wire for longer.
Good. So let's go back to this picture. If there were no collision, whatever collision resolution protocol you're using, the eventually the idea is that one node gets the channel, and that's the only node that gets the channel. No other node is transmitting, right? So eventually you want to get to a point where this kind of interference doesn't happen. If each frame, typical frames are limited by MTU sizes around 1500 bytes on most internet networks. But let's say each frame was one megabyte long. It's a huge frame. You don't want such a huge frame because bits can get corrupted. It's unlikely to even get there. MTU won't be satisfied. But just for a second, imagine each frame was 1 megabyte long. What will happen? Eventually, collision resolution will happen. One node will transmit. And once it starts transmitting this 1 megabyte, and the signal has reached after it started transmitting, the signal has reached all nodes, which happens at this point. The furthest node gets the signal. If it managed to send this much without any other node transmitting, this is only a few bits here. At this point, no other node will transmit. They are all doing the first part of CSMA, applied convolution. Somebody else is speaking, don't speak. So they will wait for the whole 1 megabyte to finish transmitting before speaking. Of course, they can collide. They can start transmitting just like in this picture. But hopefully, eventually, when it resolves, one node gets 1 megabyte of transmission time. when 100% useful activity happens. Some node is transmitting, channel is not idle, channel is not under collision. So if the frame size is long, you get more opportunity to keep the channel occupied up to exactly one node is transmitting. It's not really just the frame size, it's really the transmission time of the frame. If you had a 1 megabyte frame, but 100 Gbps, well, we don't really have 100 Gbps Ethernet. But this denominator was high, then the frame transmission time was very small. So really, the longer the frame transmission time, either a bigger frame or like a slower Ethernet in bits per second, that will increase the transmission time. The more the frame transmission time, the more efficient Ethernet is. Okay. So the counterintuitive part of it is you tend to think that faster Ethernets might be efficient, but the opposite is true. Faster Ethernets actually make the efficiency slower. All right, so the next question is, Aloha we said was just 18% efficient in the limit case. It could be as bad as 18% if a large number of runs apply. What about Ethernet? What can you say about Ethernet? Well, that's the formula. How well does it work in practice? Let's plug in some values. Let's say the frame size is the typical frame size, 1500 bytes is our favorite value because it tends to roughly match network MPUs. And let's look at 100 Mbps. This is a very common Ethernet speed, right? Most of the computer science department is on it's either on 100 Mbps or 1 Gbps Ethernet. Some parts maybe on a 10 Gbps. But let's start with 100 Mbps. Okay? Is this all we need to compute efficiency? This S and this C will give us transmission time. What about propagation time? Where do we get propagation time from? Regarding Z? Is that right? Did I type that right? 5 times propagation delay divided by transmission delay, which is this. Alright. That's how efficient state event is. Okay, this is between 0 and 1. So 0.99 nanometers is near close to perfectly efficient. So Ethernet is very, very good at resolving collisions and making sure that empty slots where no one transmits, if there is somebody trying to transmit, as well as collision slots with multiple nodes transmit, is rare. Okay? I'm a little surprised it's that close to 1, but so let me just double check. 500 microseconds. That seems okay to me. This is a 100 Mbps Ethernet. What happens if it's a 1 Gbps Ethernet? For the 1 Gbps Ethernet, you're looking at, so it should be 10 to the 9. Or let's say 10 Gbps Ethernet, that would be 10 to the 10. Change like that change. Oh, sorry, I have a mistake in the previous one. Sorry about that. Let me just recompute that. No wonder I was surprised it's that many times. It is efficient, but it's not that efficient. Okay. So that is what it is. That doesn't look me something.
On the blackboard, you wrote 100 megabits per second, is that a problem?
Or isn't that the same I did there?
On the C, you wrote, you goes 100 megabits.
Yeah,
Isn't
that's
that-
100 megabits. One more factor, then you're looking at 70% efficiency. If you go to a weaker Ethernet, a slower Ethernet, from 100 Mbps to just 1 Mbps or 10 Mbps Ethernet, you get 96% efficiency. And on the other hand, if you go to a 10 Gbps Ethernet, again your efficiency is 2.3%. I'm not confident these numbers are right, but that's what I'm getting for 800 Mbps Ethernet with this frame size, okay? But I've double checked this math, and if I find a mistake, I'll post it to Piazza, otherwise these are the numbers for Ethernet. So I would say, if you look at this number, for a 10 Mbps Ethernet with a LAN propagation delay engineered down to about 10 microseconds, which is closer to the industry state of art, you're looking at 96% efficiency for Ethernet, which is much better than a low power. But these numbers really depend on those parameters. Okay? We didn't assume any clock synchronization here, unlike, so it's similar in that sense to unslotted Aloha, non-slotted Aloha. And yeah, in terms of protocol constants, in Aloha we had a parameter P, which we optimized, that has to be set. Here really there isn't much of a protocol constant beyond 5 total times that defines that slot, right? How much you back off, the unit back off is what's defined here. Okay, so that's all is there to say about Ethernet. You've already seen how turn-taking protocols or channel partitioning protocols like FDMA, TDMA, or the Open Ring protocol work, right? These protocols were, people played around with various designs for decentralized efficient design for MAC, for multiple access control protocol. And Ethernet really won the day in this, way back from the 70s. So Ethernet is what really rules. So this is Bob Metcalf's original graphic of how he envisioned Ethernet. Bob Metcalf is credited with having invented the Ethernet. A rich person now because of that. Our speeds have grown from, actually back then, from megabits per second to tens of Gbps is common. Moving forward with hundreds of Gbps, you have to have very elaborate router designs to be able to accommodate those designs. We saw a little bit of this in switch interconnects, how we use these crossbars. You could recursively put many of those together in really high speed data centers. Okay. The Ethernet physical topology has evolved over time as well. So all of these Ethernets, where's the Ethernet protocol, carrier since multiple access protocol, is being spoken at the NIC. So it's at this point, the point in the NIC includes the cable plug. That's what's in the CSMC protocol. We've gone from a bus-based design to which using T-connectors you could have any number of machines, more to the current state of the art, which is a switch-based design. If you have set up a wireless network at home, one of the components that you probably bought in the process, or maybe your service provider, your ISP gave you, was an Ethernet switch, right? It has a few ports in it, you can connect multiple machines into it. So Ethernet switches are very, very common now. These used to be somewhat more expensive, but these are about small or $10 for a 4, 4, 6, or 8 port switch. Up to, these Ethernet switches these days go from one, at these costs go from 1 Gbps even 10 Gbps. More or faster than 10 Gbps or faster switches with many ports will cost more. So switched Ethernets are the most common form in which Ethernet is deployed. This kind of a deployment, bus days, it's not that common. You don't see them. Okay. There's a very distinct advantage to switch-based designs because they separate the collision domain. Anything here cannot actually collide with anything here, because the switch will actually temporarily keep the packet here and then decide what to do with it. In that sense, it's a little bit like a router, like a forwarding machine, like a forwarding device with the network layer, but this will actually link it. So in this design, if one node speaks, everybody can hear is not true. This is the collision domain. Whereas here, if one node speaks, everybody speaks, can hear is true. Okay. Here really it's a two endpoint. If this node speaks, if this endpoint speaks, or this endpoint speaks. Why might this endpoint speak? Because it might be sending back from here or here over to here. So it's just it partitions the Ethernet into just collision domains of size 2, which again makes it much more efficient. Less nodes are colliding, it's easier to resolve collisions. Right there is Ethernet's frame structure, header and payload, just like we've seen this for UDP, TCP, and IP. That's Ethernet. It's first followed. It starts out with a preamble. A preamble is just a well-known pattern of bytes, right? So 7 bytes of this followed by an 8th byte that is this. How does the NIC know when a frame is coming in? It is constantly sensing the wire. When it senses some energy in the wire, it will start decoding the signals into bits. Signals are just literally the sinusoids, electromagnetic signals. And the decoders are going to convert these signals, up and downs, into zeros and ones. And if it sees this 8-byte pattern, that's a preamble. It knows that this is the start of a frame. That's when it knows to latch on and know that, okay, this is where the frame starts. So as expected, in every header you have a source and destination component, which is source MAC address, destination MAC address. What are these MAC addresses? They are 48-bit addresses. They're not 32-bit like IPv4. Okay? What does the MAC address look like? So if I do, this is something you can see with the equivalent of ifconfig on your platform, on Mac or any Unix machines, command workflows. Or I have a sticky pen. Okay, so if I do this, I see a bunch of interfaces, some virtual, some non-virtual. Here is an actual Wi-Fi based IP address that the DHCP server gave me when I first got connected to Wi-Fi in this room. I didn't have this when I was in the office. When I got here, Wi-Fi gave me something like this, and that interface with MAC address is this. That is in hex, so you see 6 times 8, 48 bits total. There's 6 sets of 2 characters. Each of those 2 characters is hex. So each of those 2 characters form 1 byte. A hex is 4 bits. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F is 15. So that's what a MAC address looks like. Every single interface on my machine will have an Ethernet address and a MAC address. Okay? So here's the rest of the fields. The preamble followed by a source MAC address, destination MAC address, and then a type field that is similar to the upper level protocol field we saw in IP. How does Ethernet know whether it goes to the IP stack or some other network layer protocol other than IP? Internet or IP is not the only possible network layer that we're running on top of Ethernet. And Ethernet can exist by itself, just a link layer protocol. It can run on top of another non-IP, non-internet based protocol stack. And so that type identifies that. And the rest is just payload and CRC. So payload followed by CRC. This, remember I showed you the checksumming where the data, you attach to the CRC at the end of the data, the remainder when divided by the generator G. That's here. You divide this whole thing by G and see the remainder is 0, that's when the checksum passes. That's what's happening. Okay? Okay, we're end of time, so we'll wind up in Tuesday's class. Tuesday's class, we will also spend the last 10 to 15 minutes filling out the SRTI post-evaluation forms. It's a good idea to get that done in the class itself, because otherwise you need it. So make sure you get your laptop or any device